Throughout this course, we'll be building a BI solution, from extracting data from data sources to loading it into a staging area where we can then transform and load it into a data warehouse. We'll also be building a cube and some data mining models, as well as some alternatives for the presentation layer. But in this module, our focus will be on dimensional modeling. We'll be exploring the concepts related to designing a star schema. Later in this course, then, we'll take this design of the star schema and use it to build our data warehouse. In this module, we'll learn about the basic dimensional modeling techniques that you can use. We'll cover the basics related to building out facts and dimensions. And while we probably won't cover everything you need to know for building out an enterprise data warehouse, you will learn enough to follow the development of our BI solution throughout this course. At the end of the module, I'll also point you to some additional resources where you can add to this knowledge. After we cover the basics, we'll also explore some additional design concepts related to handling dates, as well as parent-child hierarchies, and slowly changing dimensions. We'll start by showing what the star schema is all about and why it's a good idea to use one. We'll also explore some general concepts related to dimension tables and fact tables. As we've noted earlier in this course, our data warehouse is built with a star schema design. Now, you may have heard other terms used to describe a similar concept, and that term would be dimensional model. These terms can pretty much be used interchangeably. Our star schema is a relational database design, which in its simplest form has a core fact table around which we organize several other tables called dimension tables. We'll talk about those in just a moment. The main characteristic of our fact table at the center of the star schema is the fact that it has multiple keys that are established as foreign key relationships. So you can see here product key, order date key, and so on. Now, there are many more columns that will fit on this particular slide, but if we could see the entire column set for this particular table, we would see that there would be numeric measures in here, such as sales amount or tax amounts and order quantities and so on. But what makes this a star schema is the fact that we have these foreign key relationships that join to a variety of dimension tables. Now, you may have more or less than the number of dimensions that you see here, but this example is provided to help you use a little imagination to see a star spring out of this structure. Typically, in our star schema structure, we have the fact table has a single join from a column in the fact table to a single dimension table. So here we have product and date and reseller and employee and sales territory, for example, as 5 different dimensions. So we have 5 joins established for this particular fact table. Typically what you'll find is that a fact table has a lot more rows than a dimension table, in the millions or the billions even, and relatively fewer number of columns. Now this particular star schema example doesn't show you everything you need to know about the fact tables and the dimension tables, but products, for example, you might have hundreds or thousands or even hundreds of thousands of products, but you would have millions and billions of rows in your fact table. So a dimension tends to have many, many columns that describe the entities and relatively few rows, in contrast to a fact table that has relatively few columns and many, many, many rows. By structuring our data in a star schema, we're effectively transforming the normalized data into a much simpler model. And the result is that we have a model that better supports high-performance queries. Because there are fewer joins involved than we would have in a normalized data structure, we can get better performing queries. Another advantage of a simpler model is the fact that we're using structures that make more sense to a business user. If a non-technical person were to look at the schema, they could pretty much tell where the data that they want comes from, whereas looking at a highly normalized structure that you would find in an OLTP system would be pretty intimidating. Your star schema can contain exactly the same data that you have in the OLTP system, but typically we make some choices when we're setting up the star schema design to only bring in data that we know is actually required for the information utilization. One of the benefits of SQL Server 2008 is the star join query optimization. So the database engine can recognize star joins and can further optimize queries, giving you even better performance than just the star schema can provide on just by the structural change. Star schema design is also tried and true. It's been around for a number of years and is now considered to be a mature modeling technique, and many BI tools will support it. And the good news is with the star schema design is that it allows you to evolve the structure of your data warehouse over time. Information requirements will change, and so it's a lot easier to make adaptations to your star schema than if you were building a solution totally on your OLTP system. Usually you start by designing dimension tables in your star schema design, so we'll start with that focus in our overview. We'll start with the basics of dimension design, and then we'll look at some specific issues that can be addressed by using snowflake design. We'll also look at defining hierarchies as well as setting up your primary keys in your dimensions. You can think of a dimension as being the noun of your schema. They describe things: time, product, employee. Usually when you're working out business requirements with users, you'll ask them to help you define what needs to go onto a report by using the by word. For example, I need to know sales by month, by product category, by sales region, by customer, and so on. Users are already thinking dimensionally, they just don't use that term for it. The challenge will be deciding what are really separate dimensions versus items that can be consolidated into a single dimension. For example, time is an easy one, where if I'm asking for information by year or by quarter, those are different bywords, but they're related. Year and quarter are really hierarchical bits of information. So as we're doing our information requirements gathering, we'll need to be sensitive to distinguishing between dimensions versus items that would be separate levels of a particular hierarchy within the same dimension. The way that I like to think about it is placing my objects for analysis on a spreadsheet. What am I going to place on rows and what am I going to place on columns? Now it's true that I could put year on rows and quarters on columns to do quarter over quarter analysis, but more commonly we're going to be doing dimensional analysis by items of different dimensions. And so those are the bits of information that we're trying to uncover during the requirements gathering process. Dimension tables have columns, of course, and we call those individual columns attributes. Each attribute describes the entities in additional detail. So for example, if we have the product dimension, which we show here as dim product, it has columns for the product name and for product color and class and style and so on. Those attributes may or may not be something that I put on rows and columns for analysis, but they might be something that I'd want to include for reporting purposes, to display in a catalog listing, for example. Or maybe with date, we have things that we would want to include for hierarchical groupings, such as year and quarter and month, so on. Typically, when we're building attributes for hierarchies, we're looking for things where there's a one-to-many relationship between the values in those columns. So with year, we have a one-to-many relationship with quarter, and from quarter we have a one-to-many relationship to months. You can also see in this example that we might have translation information. So we might track things in English and Spanish and French, for example, to be able to support global analysis.